All right, so what I'm going to do is go over some worksheets I have, and I've got the answers as well. And give you an idea of what a typical test question it might look like. Now, remember with carbohydrates, you've got monosaccharides, got disaccharides, oligosaccharides, polysaccharides. And so 2 or 3 out of each one of those you need to know. Let me get down here to these are the answers. Okay. So, as like all tests, you're going to have naming structures, you're going to have reactions, and you're going to have intermolecular forces. Intermolecular forces is always the minor part. And reactions are the ones you need to really focus on. They're the ones that give students the most trouble. All right, so let's go ahead and go through these. Okay. I want you to remember now with carbon backbones, we're starting to get into primary and secondary backbones. And I use different colored highlighters to indicate which is which. The primary backbone, I always do use yellow. It's going to be this guy here. Remember, the backbone has got to contain the functional group. And this is a 1, 2, 3, 4, 5, and it's a ketone. So it's going to be a 2 pentanone with a methyl branch at 1, 2, 3, 4. So 4-methyl 2-metanone. Okay. Now a colleague of mine did these worksheets, and he always puts the H in the aldehyde. I usually don't put the H there. I usually just put the carbonyl on the end. But remember, there is the carbonyls on the end. There is an H there. That means it's susceptible to oxidation. Okay, so it's an aldehyde, and it's a 1, 2, 3, 4. So it's going to be a butanol. We have 2 bromo branches, so it's dibromo. So 2,4-dibromo butanol. Now, some people have been asking me, do I need to put the 1 there on the butanol? I like to say it's optional, but if you put it in, it'll be totally consistent with the ketone number, even though an aldehyde has to be on the end. No exceptions. Has to be on the end. But you can have a dial or a trial. Now, one of the a little side note, when I first went into graduate school, first thing you do is you take your oral and all that stuff is extremely horrendously high pressure. But anyway, once you have that, you have to figure out who your principal investigator is going to be. So they have to have money. If they don't have a lot of money, then you have to TA, teaching assistant. Well, you can also be a research assistant which means you get the same amount of money, but you don't have to teach. So what I did is I went to all these professors. I should say most of them, and told them I was interested in their program. And some of them had money, some of them didn't. Some of them had programs that I wasn't really interested in. Anyway, this one guy came up with this very interesting point. If you've got a fatty acid and you've got a double bond in the fatty acid, that is, as you remember, double bonds are not very stable. So whenever you get any kind of energy, external energy, they will oxidize. Well, that ends up doing something like this. That oxidized to that 3-carbon dial. And it's named malonaldehyde. And he needed a student to have that as their dissertation. Well, I thought it was pretty cool. I did some research on it. I found out that this is a cross-linking agent for DNA. What that means is it can be a carcinogen. And if it's a carcinogen, these get made all the time. All the time. If you put lotion on your body and go outside in the sun, guess what? You make malonaldehyde. Malonaldehyde is very bad for you. But no one knew how to figure out why it was so bad. And that was the whole function of that dissertation topic. But the guy had no money, so I was interested in the topic, but I had to get money. I ended up working with a guy who did undergraduate research. He had tons of money. He was a lipid chemist, and he had about 12 graduate students in the lab, a couple of postdocs. He had tons of money. So sure, come on, and he was used to me and stuff. So I ended up doing that. But if you're thinking about graduate school, that's kind of the way it is. There's a topic, and then there's money. You need to decide what you want to do in that. But this aldehyde was particularly awful. And the more I studied it, the more I was going like, oh my gosh, this is truly bad. And guess what? The more double bond you have in the fatty acid, the more susceptible it is for oxidation. Who in here cooks? Anyone? Okay. Notice on your bottle of vegetable oil, when it gets towards the end, it kind of gets stickier on the top. And guess what that is? That's when fatty acids polymerize. When they polymerize, start making this kind of stuff. So that's why a lot of people talk about seed oils being bad for you. That's like canola, corn oil, vegetable oil, soybean oil, as opposed to olive oil or lard or tallow. All of old-fashioned fats. So anyway, that's an example of a dual aldehyde. Nasty one. Okay. All right, let's go ahead and go on here. So if you want to put one butanol, that's fine. Okay, let's go on here. Okay, we have now whenever we have a cyclic compound, you cannot have an aldehyde. Unless it's a branch. But if it's on the ring, there'd only be a ketone. So immediately you go, it's cyclic, so bam, ketone. And it's a 5-membered ring. cyclopentanone. And then we have two branches at carbons 1, 2, 3, 4, 5. So 2, 5. Two, 5 dichlorocyclopentanone. Okay, we have another ketone over here. And it's 1, 2, 3, 4. So it's going to be a butanone. And we have a 1-phenyl. That's this guy here. One, two, three. Oops, I guess the three's over here. 3-methyl. 2-butanone. Okay. All right, draw the following structures. Okay, so we've got a six-membered ketone, cyclic. And automatically the ketone is carbon number 1. And at position 3 is a methyl. During lab today, by the way, and Thursday, I'm going to post, because there's a lot of downtime in this lab, because you got to wait till your stuff boils and has to go through a distillation column, etc. And I'm going to start putting practice problems up on this projection screen. So you can do those while you're waiting for your distillate to finish. Okay. For this guy here, we've got a butanal or carbon aldehyde. Okay, we've got a branch at carbon number 3 and 4. Okay, I'm going to skip number 7. It says draw structural formulas and provide the IUPAC names for the aldehydes and ketones that have the molecular formula. That's just a matter of coming up with 3 simple aldehydes or ketones. Okay, hydrogen bonding behavior. Okay. So this is an aldehyde. And if you have a carbonyl group, a C double bonded O, where that electrophilic oxygen draws electrons from the carbon, you end up with a dipole there. And that's attracted to the hydrogen in water. Okay, it says write an equation using structures for the formation of the following compound from the appropriate alcohol. So this question, you're going to start with an alcohol. You want to end up with, this is a carboxylic acid here. Okay, so let's see. Do I have the flow chart? Yeah. So here we have the acid right here. And that means we're going to oxidize a aldehyde. And that aldehyde is going to come from a primary alcohol with the same carbon backbone. And remember, I always give you the flow chart on the test. Okay, so let's go back to here. Okay. So we're going to start with an alcohol, and we need to start with the basic carbon backbone. So this has got this guy here would be the primary. And then we have a branch off of that. So let's so we want to start from the alcohol with the same structure, basically, okay? So what happens to the primary alcohol if we oxidize it? It forms a aldehyde. So let's see, let's do this a little differently. Okay, and then that will continue to oxidize from the aldehyde to the acid. Now, this is a typical dilemma a synthetic chemist faces. Okay, I think I want to make this a new drug on the market, right? I want to make it. What can I start? Well, acids can come from oxidized aldehyde, which can come from oxidized alcohol. Okay, well, let's start with the alcohol and then oxidize it. Now, life in a lab is like this. You oxidize it and you think you have this stuff. You don't know it, but you have to do a bunch of tests to determine if that structure is really what you got. But you always have other junk. You have leftover starting materials, you have oxidizing agents, all that stuff pollutes your nice aldehyde here. But then you have to come up with ways which takes usually more time, more money, more effort to clean up this aldehyde. Now we're going to run into this when we make aspirin. Aspirin starts with salicylic acid, and we're going to end up making an ester, which is aspirin, and a whole bunch of other junk. So we're going to go through a number of purification steps, get rid of the other junk. And then we're going to test it in the instrument room to see if you really have aspirin. Or if you don't have aspirin, what do you have? That's a typical challenge for synthetic chemists. And drugs, I don't know if you've ever looked at the structure of some of these drugs, they are really complex. frequently organic chemists will protect. For example, aldehydes are very reactive. So if you want an aldehyde, you have to protect it first. Some other stuff attacking it. Frequently, that's an intermediate step. And then you have to recreate it, which is unprotected. There's a lot of wild steps you have to go through when you're making stuff. And the more pure it is, they have extra purification steps, meaning more expensive. Okay, are there any questions about this? Primary alcohol, oxidized aldehyde, oxidized to the acid. Yeah.
How would you name those like structures like the alcohol?
So why don't we name the alcohol? We haven't got the acid yet. That's unit 3. So let's name this guy to start with. Okay. So okay, it is a 1-carbon alcohol. With a branch, and let's simplify this a little bit. So it's a 1-carbon alcohol with a phenol branch. So it's one phenol methanol. And then if we wanted to add the original substitution out here, you say it would be 2 propyl dash 1 phenol methanol. That makes sense? Yeah. And this would be methyl. This would be carbonic acid. Okay, so it's important to have your flow chart in front of you whenever you're doing reactions and understand how to use it. Some teachers will not give you that flow chart unless you'll be able to use it as a tool as opposed to memorizing it. We've got enough structures to memorize in this class without memorizing that whole chart. Okay. All right. More reactions, good old reactions. Okay, so what we have here is a ketone, and we've got a hydrogen with a platinum catalyst. And that is the same thing as a reduction environment. So make sure that's in your notes. So on your flow chart, when you see R, put H2PT. Okay, so what does a ketone in a reductive environment look like? So if the arrow points for oxidation, the opposite of oxidation is reduction. Yeah.
Oh, where in the files is that flow chart?
It's under Canvas, File, Unit 2, towards the bottom. If you get into Unit 2, it's a bunch of, but it's towards the bottom. Okay, so every time there's an O here, we can make a backup arrow. Then R. So the opposite of oxidation is reduction. So an R means Reduction means adding hydrogen. Oxidation means removing hydrogen. On 305, we talked about oxidation and transfer of electrons, losing electrons. In organic chemistry, we substitute H's for electrons. So if we're adding hydrogen, that's reduction. So losing hydrogen, oxidation. Rarely, when you read a biochemical journal, they'll talk about electrons. Unless you take 420 and 421. And they talk a lot about electrons underneath the covers, what's going on. A high level reactions, we talk about hydrogen. Okay, so we're going to be using this path here. All right, where did I leave off? Let's see it. Ah. Hmm. Okay. These are also under Canvas files worksheets, unit 2. So you've got practice tests and worksheets with and without answers. Okay, so we're going to reduce the ketone there, which produces a secondary alcohol. Bless you. Now that's a dicyclohexane substitute branches. Okay. Now, if we put this in an oxidative environment, would anything happen? What will we get or not get? Can ketones be oxidized? That's right. She's shaking her head no. That's correct. It cannot be oxidized. So nothing would happen, only in a reductive environment where we would see that ketone being reacted. And then we introduce, remember, for oxidation to occur, we have to lose that hydrogen. When reduction occurs, we add the hydrogen back in. So now we have a hydrogen right there in that carbon. Okay? Yeah.
So it's not going to happen every time it would be a reaction because, well, it's not.
Yeah, because there's no hydrogen. Oxidation is part of the hydrogen. There's none there to leave. So ketones are very stable. Aldehyde have a hydrogen there, but they can be further off. So that's why ketone reactions are really different than aldehyde reactions. Aldehydes are not very stable. That's why that 3-carbon double aldehyde is particularly bad. And not only have an aldehyde, it's two. Yeah.
How do you need to know how to name that? How would you? said like.
Yeah, it's- What kind of things am I gonna listen? So if I, we've got a di cyclo hexyl methanol. And I probably wouldn't ask you to name that. That's pretty big. Okay, any more questions about oxidation reduction? Happens a lot in nature. Our bodies, via enzymes, undergo a ton of oxidation and reductions. The whole unit 5 on carbohydrate metabolism. What happens to glucose as it goes through glycolysis, Krebs cycle, and oxidative phosphorylation, producing ATP? Whole bunch of oxidations and reductions. A whole bunch. So just keep that in mind. Hydrogens come and hydrogens go. Hydrogens are coming, it's reduction. If they leave, oxidation. Okay. All right, let's look at this guy. Now, this guy is a little trickier. Because we have an OCO. With an anomeric carbon there. So we have OCO is yes. Okay, do we have hydroxyl? Yes. And do we have a hydrogen? No. Okay, so no hydrogens means it's either a hemiketal or a ketal. Hydroxyl means it's a hemi. So it's going to be a hemiketal. I'm sorry?
Can you repeat that again?
Okay, there's the test for acetal and ketal. 3 tests. OCO, yes or no. If it's yes, then you do the other 2 steps. So is H present? Yes or no. In this case, no. That means it's a ketal of some sort. And if OH is present, it's a heavy ketal. And the carbon is the anomeric carbon. That means everything revolves around that anomeric carbon. Okay, and you don't have to name acetals and ketals. You just have to say it's an acetal or ketal or whatever. Okay. All right. So we're starting with a hemi ketal. And we're going to throw an alcohol on there. So we have secondary and primary backbone. So primary is going to be where the anomeric carbon is. Then it's going to be a 1, 2, 3, 4. Primary backbone. Then we have a secondary backbone on that alcohol over here. I'm going to be adding a 3-carbon alcohol to it. And that's going to replace the OH. So you redraw the primary, secondary backbones. Okay, so that's 3 carbons. Anomeric carbon there. Oxygen. Methyl group. Okay, that's going to be secondary. Primary. Okay. And the OH is going to be substituted by that alcohol. So that's a 3-carbon alcohol. So now we have OCO No OH and no H. Hence, that is a ketal. Now, there are four. If you get an OCO, you've got four deals to figure out. Hemi, there's two hemis and two non-hemi. Either a hemi-ketal or hemi-acetal, or a full-blown ketal or an acetal. Ketals come from ketones, acetals come from aldehyde. Yeah.
The first part with reaction and test, do you expect us to name anything in this part?
You don't have to name the ketals or acetal unless I ask you, is this a ketal or acetal? Because then you get into the methoxy and all that stuff. It's, for me, the reason I have you name stuff is so you focus on the structure. And it defeats the purpose when you get so crazy on the naming it. But there's absolutely an IUPAC name for it. Yeah. The pink.
Why is it like split up?
Because whenever you have an alcohol reaction with a ketone and aldehyde, yeah, the first one, and then you have a subsequent one. First one's the hemi, whatever, and the next one is the full version. And the alcohols that are adding to the main backbone are the secondary backbones. And I do it in pink rather than yellow. Better, a little better. Okay. Now the problem with acetyl and ketal is that is the chemistry of carbs. In carbs, you've thrown all these wild structures, but it's the basic chemistry of acetals and ketals. Okay, let's go on here. Any more questions about that? This means you add that twice. So let's add it once. What do we get? Okay, we start with an aldehyde. Starting with an aldehyde. So that means we can either get some kind of an acetal. We're starting with an aldehyde. It's either going to be a hemiacetal or a full-blown acetal. Okay, the first one. So it's a 3-carbon aldehyde. And we're adding to that a 3-carbon alcohol. Oops. The secondary. Okay, so what does the first one look like? Okay, so the OH is going to attack the carbonyl group, the C double bonded O. So we're going to end up with a 3-carbon, and that's the anomeric carbon there. So we're going to end up with the original 3-carbon backbone. And we're going to have a hydroxyl group plus the 3-carbon alcohol. Let me modify this slightly here. Okay, so that's going to be the hemiacetal version. Now we're going to add another 3-carbon alcohol. Okay, so this is an aldehyde. That's the anomeric carbon. We're going to have OCO. We're going to have hydroxyl yes. And because it's starting with an aldehyde, we're doing hydrogen. So that means this is a hemiacetal. Now I'm going to throw another alcohol into that. When I stop talking, it always gives me this. Hey, you're not talking. Okay, so that's going to replace the hydroxyl group. We've got the 3-carbon anomeric carbon there. And we've got the original deal here. And then we have another one over here. So that's the original 3-carbon aldehyde. And then we have the 2 alcohols that were added. Again, keep track of the anomeric carbon. And that's what actually takes place when we're talking about adding alcohol to a ketone or aldehyde. Okay, so that's the OCO, the C in the middle is the anomeric carbon. That's carried throughout. In this case, we have hydroxyl group and hydrogen here. Okay. And then it's a hemiacetal. It's important to be able to identify hemiacetals. The carbohydrate ends up being a reducing sugar. That's always a question I ask. Is this a reducing sugar? Technique, find the hemiacetal if it exists. If it exists, that means the hemiacetal can open up to an aldehyde, hence it can be oxidized. Okay, so this analyzes this OCO. We've got OCO, and we've got hydrogen there, and no OH. That means that is now a acetal. Acetal will open up. Hemiacetal will do. So if you've got a couple monosaccharides stuck together by acetals, that means those aren't moving. If at the end of that string is a hemiacetal, it can open up and be oxidized. And that's a reducing sugar. It is always a question on carb exams. Is this reducing sugar? Why? When you say yes, there's a hemiacetal, circle it. Or no, there's no hemiacetals. Okay, so all these are simple acetal ketal reactions. I tell you what, on Thursday, we're going to focus only on carbs, more complex structures. And today, let's focus on the non-carbohydrate acetal and ketal reactions. There's quite a number here. Okay, so we've got this is basically 13 is the same reaction as number 12, an aldehyde, and we're adding methanol. Same exact reaction all the way through. All right, let's go on to 14. All right, so we've got a cyclopentanone. So this is a cyclopentanone. And we're going to oxidize it. What's going to happen? Nope. No hydrogen there. What's going to happen? Nothing. Ketones cannot be oxidized. Period. So no reaction. Okay. Now, what have we got here? Well, we've got a ketal. How do I know that? Okay, we have OCO. We have no OH and no hydrogen there off of the anomeric carbon. That means it's a ketal. Ketals can come apart in an acidic environment. Comes apart to the alcohols in the original ketone or aldehyde. Okay, so let's look at, that's the primary backbone. And this would be secondary backbone. So we've got a 1, 2, 3, 4, 5 carbon backbone. And the primary backbone does not change. It's carried throughout either the oxidation phase or the reduction phase. And then we have first one alcohol comes off, leave in OH. And then under further reaction, the second alcohol will come off. So we end up with the original ketone. So backbone plus another alcohol. Now it's important to keep the secondary and primary backbones separate. Highlighted. The primary backbone is carried throughout the whole thing. The secondary ones come and go, depending when you're adding the alcohol or taking it away. But the primary backbone does not change. Okay, does that work for you guys? So we can form ketals and acetals, we can also take them apart. When we take them apart, we end up with the original backbone, aldehyde or ketone, plus alcohols. And number 16 is the same reaction with a different backbone. Okay, so now we have multi-step synthesis. In other words, this is not a one-step. So how do we get to that? Well, first of all, what is it we're going to make? Well, we've got an OCO. CO right here. And we have an OCO, that means you have an anomeric carbon. Okay, as soon as we have an OCO, that means we need an aldehyde or ketone plus some alcohol. The alcohols are one carbon alcohols, methanol. And then what do we have here? Well, let's look at this. H, yes or no?
Does it count? H3O, does that count or no?
No, it's gotta be in the anomeric carbon. So H, yes or no? No. OH. Anomeric carbon, no. Okay, so this is a ketal. Ketals come from ketones. And these are one carbon alcohols. Okay, well, let's back up now. How do you make a ketal? Make a ketal from a ketone. All right? And this going from here to here requires that. In other words, we're going to take the ketal apart. And we take the ketal apart, we end up with some alcohol. So this is going to be the original secondary. And we end up with two of them. Okay. All right. So that gets us to a ketal, but we're starting with an alcohol. How do we get to a ketone from an alcohol? What makes a ketone? We oxidize a secondary alcohol. So we start with cyclopentanol, oxidize it to cyclopentanone, and then from here we add two alcohols, the two methanols. We end up with a ketone. That's going to have one multi-step synthesis. We have one intermediate step. Now, as an organic synthesis, sometimes you have 10 intermediate steps. Depends what you're trying to make and what you can start with. Okay, and here we're just going to have one of them. It'll be the simplest multi-step possible. Okay? one step in between. Okay, now let's look at this next one here. This is another multi-step one. You start with a ketone, and how do we get an alkene from a ketone? What do you think we should do? Well, what are the ways to get an alkene? There's a couple ways. The main way is starting with an alcohol. And you pull the alcohol off and you double bond. Okay, so what alcohol will we need to make this cyclic alkene? Okay, so 180 degrees, sulfuric acid or H plus will give us that alkene. Wine reaction. Okay, well, how do we go from a ketone to a secondary alcohol? Reduction. Okay, so let's look at flow chart. Where is the flow chart? Okay. So here we have the alkene. Oops. There's the alkene. And we take the alcohol at 180 degrees in an acid solution. We're going to end up with the alkene from the alcohol. Okay. And then how do we get the alcohol? We go opposite oxidation, which is reduction. I'm going to take a ketone because it's a secondary alcohol and reduce it. This is why everyone says the hard part of the test in the slides are reactive. Okay, so we go back up to here. We're going to take the ketone, reduce it, we end up with an alcohol. We take the alcohol under 180 degrees, acidic conditions, we end up with an alkene.
When you think it's out, right now the process, would you want us to make the mix since it can double bond?
There is a mix, except it ends up being the same molecule.
Okay, so it doesn't.
In this case, it is. But yes, there is a mix. It's just like you can't tell the difference between the two. If we had a methyl group here, then you definitely get it.
And then would you also mention that?
Yeah. Okay. Okay, so that is a really good, review of non-carb aldehyde ketone chemistry. Okay, there's some synthesis there with multi-step synthesis, we have naming, we have structures, and a little bit of intermolecular forces. Now, on Thursday, we're gonna do the same thing with carbs. Okay, so between now and Thursday, I have to really put some time in here. Just as a week from today. And most people feel this is not the hardest test, but the most detailed of the 5 tests because of the structures of the carbohydrates. Flashcard city. And remember the carbs now you have monosaccharide, fructose, glucose, maltose, disaccharide, maltose, lactose, and sucrose. Then you have raffinose, which is the illegal saccharide, and you have starch and cellulose, but a polysaccharide. Those are the most common carbs ever. And then there's a whole bunch of variants in there. Those are carbs you need. Okay, let me list those again. If you look at the presentation last time I mentioned in the slides, I'll see them all. Okay, that's what I wanted to cover today. It was a lot. You need to practice and use a highlight. What's your backbone? It's carried out to the reactor. And the primary backbone and secondary backbone carried throughout the reaction. Now, I wanted to end a little early today because the lab can be long, depending on, we've got a very complicated glassware setup for this lab. Then you've got to take and get the orange part of the peel. And really taking this and zesting it. You cook it all, you know about zest. No pith. White part. Only orange part. And we're going to then take that zest of the orange and reduce it down to essential oil. And that's what we're going to use in our soda. All right, any questions about this guy? All right, here. Yeah, we're going to start lab early because it can be long. It depends. There's a lot of variables.
Some experiment procedure for the last week's lab with alcohols and phenols. This is steam distillation.
Okay, this looks good. The only problem is you might not have looked at it. So don't, if you need more space, just use the back.
Yeah.
That's one of the reasons why we left the back open.
Yeah.
So in case you need it, you got it.
They're both constants, right?
And never your page.
Yeah, yeah.
This looks good. And name on the front.
And then in terms of like, for example, the lab itself has questions, that is not going into the pump, but that's just gonna get filled out on the paper.
Everything goes in there.
Okay.
Because that's what you're going to scan out.
Gotcha, okay. So basically, whatever questions are on the pages, we don't answer them on the pages, we transfer it over. Okay. All
And you
right.
don't have to write the whole.
Just the answer.
The answer kind of included in the question, like what's the color of milk? White. So you can say milk is white. So you
Yeah.
included a question in there.
All right, makes sense.
Cool.
Thank you.
So everyone goes in your lab notebook.
Okay, so this would be the questions after, like the procedure section or before the procedure?
This is as long as they're.
Okay.
So the pre-app questions are part of the pre-app.
Right, okay, thank you.
Get our goggles and that jacket for that.
In your fancy coat. Did you tie dye yours?
Have my lap jacket. So.